morning everyone. I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next topic, that is fading for the subject, that is wireless and mobile communication. The topic of today's lecture are having introduction of fading. Then there are two types of fading that exist, that is large scale fading and small scale fading. So, we are going to discuss this in detail. So, first we will begin with what is fading. Fading exists in my previous lecture I have also discussed what is fading. Fading exists in multipath propagation, because in urban areas and suburban areas there is no direct line of sight exist between the transmitter and receiver. There will be a building, hills and other intermediate node exist, like in this example you can see that this is the transmitter, this is the receiver, and we have to transmit a signal simply from transmitter to receiver. Now, due to multiple hops that exist, like this is a building, these are the hills, this is a tree. So, the signal will be received from multiple paths, and you can see that you have transmitted this one and you are getting this signal which is having ISI, that is inter-symbol interference, and this is much more distorted as compared to the original signal. Its characteristics is totally changed. So, that is known as it undergoes fading. The signal strength or the power gets reduced due to this multipath fading. So, there are two types of fadings are there. First one is the large scale, second one is the small scale fading. So, this diagram is basically showing, this chart is basically showing that what are the different types of fading. Sorry, this one is the large scale fading, this one is a small scale fading. In case of large scale fading, it is mean signal attenuation versus distance. This is variation about the mean. So, whatever mean you have calculated, that is denoted by mu of a particular signal, you have to consider for calculating this large scale fading. In case of this small scale fading, this is divided into time spreading of the signal and time variance of the signal. So, both these things are considered. In case of time spreading of the signal, it has this Fourier transform pair, that is time domain and frequency domain. These we are going to study, that is frequency selective fading and flat fading. In case of this time variance channel, there will be slow fading and flat fading, both in time domain and frequency domain. So, this we are going to discuss in detail. So, there are two types of fading, large scale and small scale. In case of large scale, we are going to consider the mean of a particular signal that we have used, and in case of small scale fading, we are using this flat fading, frequency selective fading, fast and slow fading. So, what is the difference basically exists between the large scale and the small scale fading. So, this diagram is showing the difference, like this is the diagram A, which is showing the transmitter and receiver. Since the distance between the transmitter and receiver is quite large, so it undergoes this free space path loss, shadowing will be there. This is the transmitter which is having this BTS, that is denoted by base transceiver station. It will going to radiate the signal. Now, this is known as forward channel. So, in case of mobile communication, there are two types of channel exist, forward channel and reverse channel. Forward channel means the signal is transmitted from the base station to the mobile. In case of reverse channel, the signal is transmitted from mobile to the base station antenna. So, this is the free space path loss, this is the signal that has been radiated, this is small scale and this is small scale fading, means the signal, the transmitter exists at very small distance from the mobile phone. In case of large scale fading, the distance between the transmitter and receiver is quite large. So, this both are characterized based on the distance d exists between the transmitter and receiver. So, the signal strength due to small scale fading, you can see that this is the strength of the signal and this is the signal that is received due to the large scale fading. In both the cases, the signal quality will going to degrade due to fading. Now, this is the graphs which are showing the large scale fading. So, this is a signal strength versus time graph, that is on the logarithmic scale, this has to be added. Now, this is the average attenuation is exponentially proportional to the distance, and this is the shadowing diffraction secondary wavelets wrap around the large object. So, this is on the linear scale, this is on the logarithmic scale, these are the buildings, this is the mountain, and when these both are added together, we are having this large scale modeling. So, large scale fading is there between the between the transmitter and receiver. Now, next is small scale fading. In case of this small scale fading, you can see that this is a stationary object, this is the receiver in moving vehicle, this is Doppler shift that has been caused by the angle of arrival relative to the motion of the receiver, and this is the stationary object. Since there is no direct line of sight exist, so this is an LOS, means it has been impinges on a building. This is also non line of sight exists between the transmitter and receiver, because there is a moving object, this is not stationary. When the receiver is moving in nature, it is not stationary, there exists a Doppler shift. Doppler shift is basically is known when let us say I am transmitting a signal, it has to be received by a receiver which is moving in nature. When the object is moving towards the transmitter, then the frequency of the signal gets added. When it is moving away from the transmitter, then the frequency of the signal gets subtracted. So, that is known as the Doppler frequency, or you have to calculate the Doppler frequency due to Doppler shift. So, this is not line of sight exist there, this means there is line of sight exist between the transmitter and receiver, this is the receiver in moving vehicle. So, this all are a part of multipath propagation. Major reason is for small scale fading is random frequency modulation due to varying Doppler shifts on the different multipath signals. So, since this is moving in nature, it means that the Doppler frequency that you have calculated either by adding or either by subtracting, these frequencies will change, because it is not stationary. It is possible sometimes that the signal will be received at 90 degree, then it is received at 180 degree, then it is received at 270 degree. So, the degree of the signal means this, I am talking about this angle, the degree of the signal gets changed, because let us say this the object will be here, then the signal will be like this one, this is another angle, then it will move towards here, then the signal is this one. So, the angle every time you can calculate, the angle will change. So, all these signals will be added at the receiver, and that undergoes multipath fading, and that is known as small scale fading. Next reason for this small scale fading is the time dispersion caused by the multipath propagation delays due to the nearby objects. So, whenever the two objects are nearby, then there will be time dispersion exist. Then movement of surrounding objects is also a reason for small scale fading. Now, next is the delay spread and inter-symbol interference. Now, delay spread is basically when the signal will be transmitted and it will be spreaded, every signal will going to spread due to the effect of noise, which will change the amplitude of the signal. Like this one is the direct signal, you can see that line of sight exists between the transmitter and receiver. This is the direct signal, this is the reflected and delayed signal. Now, you can see that amplitude of signal and this signal gets reduced due to the reflection, and it is delayed version. So, whatever it is been shown over here, this is the delayed version of the first one. This is the received signal showing the multipath. Now, you can see that here there will be noise that have affected the signal quality. So, that will be the drawback of delay spread and the effect of inter-symbol interference, which is been shown in these waveforms. Now, next is some of the definitions that is being used to see the small scale fading. Like first one is the coherence bandwidth. Now, for a reliable communication without using the adaptive equalization or other anti multipath techniques, the transmitted data rate may be much smaller than the inverse of the RMS delay spread. Now, RMS delay spread means root mean square value that you have calculated after seeing the delay spread, which I have shown in the previous slide. Now, it is called the coherence bandwidth. The channel transfer function remains virtually constant over the coherence bandwidth. So, that is known as coherence bandwidth. Next one is the resolvable path. Now, a wideband signal with symbol duration T s or a direct sequence, that is denoted by D s CDMA signal with chip time, that is denoted by T chip, can resolve the time dispersion of the channel with an accuracy of about T s. So, this is the resolvable path, that is denoted by N p is equals to round trip time of T delay, that is the delay time divided by the chip rate time, that is the T chip plus 1. So, this is the formula for N p, where round is the largest round is nothing, it is the largest integer value smaller than x, and T delay is the total length of the delay profile. So, these are the two parameters that are required. Now, round means you have to round off the value nearest to the integer, like if it is after decimal, if it is greater than 5, then you have to round it to the nearest value. If it is less than 5, then you have to keep it the value same. So, that is known as resolvable path. Now, wideband signal with symbol duration T s or a direct sequence D s CDMA, its chip time can resolve the time dispersion of the channel with an accuracy of T s. So, T s is nothing, it is the accuracy time of a particular signal. Now, next this is showing the Doppler shift. Now, Doppler shift basically plays an important role when the receiver is moving in nature, when the signal has to be received by a moving object. Now, you can see that this is a base station, this is tall building, this is another building, this is stationary object, and this is a moving vehicle with a velocity of having some value. Now, you can see that whatever signal, since this is moving in nature at let us say at time t 1, this is present over here. So, whatever signal will be received is added together. Now, at another point of time, let us say t 2, this particular receiver will be present at this point, then obviously, the signal angle will be changed because it has to be delivered over here. Now, next at time t 3, the object will be present over here at that is the receiver. Now, again the signal will have to be changed. So, that is known as Doppler shift, which plays an important role when the receiver is moving in nature. Now, this is the characterization of small scale fading. Now, small scale fading, I have told you it is of 4 different types, that is flat fading, frequency selective, fast and slow fading. So, based on the multipath time delay spread and based on the Doppler spread. Now, Doppler spread and multipath time delay spread is something different. In case of multipath propagation, in the first case, we are considering that the receiver is not moving in nature. In case of Doppler spread, we are considering that the receiver is moving in nature. So, in this case, multipath time delay, this is known as the flat fading. Its bandwidth signal is smaller than the bandwidth of the channel, and then delay spread is smaller than the symbol period. So, this is how we have to characterize the particular signal, with that bandwidth of the signal is smaller than the bandwidth of the channel. So, this is required because in case of let us say there are 4 stations exist like S 1, S 2, S 3 and S 4. These 4 signals has to be transmitted and it has to be received at the this will be transmitted, this has to be received at the receiver side. So, these the bandwidth of these individual users are known as signal bandwidth, the bandwidth of channel is known as channel bandwidth. So, channel bandwidth should always be greater than the signal bandwidth in case of flat fading. Also, the delay spread is smaller than the symbol period. So, these are the 2 points that you have to keep in mind for the flat fading. In case of frequency selective fading, the bandwidth of the signal should be greater than the bandwidth of the channel. That is the reverse part of flat fading, and also the delay spread should be greater than the symbol period. So, these 4 things you have to keep in mind, and which value should be greater than, which value should be smaller than, that will going to change the flat fading and to small frequency selective fading. Now, based on the Doppler spread, since the object receiver is moving in nature that we have considered in this Doppler spread, it is possible that we have to see the what will be the speed of the moving object. Maybe it is fast moving object, maybe it is slow moving object. So, depending on that, the fast fading and slow fading comes into the picture. Like in case of fast fading, the high Doppler spread will be there, its coherent time is less than the symbol period. Also, the channel variations are faster than the baseband signal variation. So, whatever variations will be there, like the channel variation or the baseband signal variations, that will be faster in case of fast fading. In case of slow fading, this is having the low Doppler spread, and this is coherence time is greater than the symbol period. The channel variations is smaller than the baseband signal variation. So, what I have told that we have to consider the speed of the object which is being considered for that particular transmission. Now, next is flat fading. We will going to discuss this in detail, these 4 things. Like first one is the flat fading. In case of flat fading, it occurs when the amplitude of the received signal changes with time. For example, according to the Rayleigh distribution. So, Rayleigh distribution is basically used to model an indoor channel model, which has their specified PDF, that is a probability density function, and that will be used for designing a fading channel. Now, it occurs when the symbol period of the transmitted signal is much larger than the delay spread of the channel. That is what written in the graph also. Then bandwidth of the applied signal is narrow in this case. Now, it causes deep fades, because in case of flat fading, since the signal bandwidth is smaller than the channel bandwidth, it undergoes deep fading, means it will increase the transmit power to combat this situation. So, basically there will be deep fade that the signal will undergo, and it will going to increase the, we have to increase the transmit power. So, that whatever loss will be there on the channel, it will be come back together. Now, this is the diagram. This is the input signal, that is denoted by ST, this is the received signal, that is denoted by RT, and this is nothing, it is the impulse response of the channel, that is denoted by HT comma tau. Now, the signal duration of the input signal is from 0 to Ts. Now, 0 to tau is the channel impulse response, and this is 0 to Ts plus tau. Now, this is Bc, that is denoted by the coherence bandwidth, Bs is the signal bandwidth, this is symbol period, this is the delay spread. Now, it occurs when Bs is far less than Bc and Ts is far greater than sigma tau. So, this is what you have required. Now, you can see that since the signal will be affected due to this particular distribution, its shape will be changed, it is considered as a trapezium. Instead of this sharp transition that will exist at this point, there will be a slow varying signal will be there. Next one is the frequency selective fading. In case of this frequency selective fading, it occurs when the channel multipath delay spread is greater than the symbol period. So, symbol faces the time dispersion, channel induces the inter-symbol interference, that is ISI, bandwidth of the signal is wider than the channel impulse response. So, this is what the frequency selective fading looks like. Now, you can see in this case as compared to the previous flat fading, it has a parabolic kind of channel impulse response. When the signal will be passed through this particular channel having which is having this particular transfer function, its shape will gets changed. Now, this will be 0 to Ts plus tau. Now, this is the input signal, this is the received signal, this is Ht comma tau. Now, it causes the distortion of the received baseband signal, it causes inter-symbol interference also, that is ISI. Now, as a rule of thumb, Ts should be less than sigma tau. It occurs when Bs is greater than Bc and Ts is less than sigma tau. So, this is the frequency selective fading concept. Now, next is the fast fading. In case of fast fading, we are using the Doppler effect. Now, Doppler effect is there when the receiver is moving in nature and also when the receiver is moving at a faster speed. Now, due to the Doppler spread, the rate of change of the channel characteristics is larger than the rate of change of the transmitted signal. So, since it is moving at a very fast pace, then the rate of change of the channel will be quite large as compared to the rate of change of the transmitted signal. The channel will changes during a symbol period. The channel changes because of the receiver motion. Since the receiver is moving in nature, then the channel will change its characteristics. Now, coherence time of the channel is smaller than the symbol period of the transmitted signal. So, it occurs when these 2 points you have to keep in mind, like the bandwidth of the signal should be lesser than the Doppler spread, symbol period should be greater than the coherence bandwidth. So, these 4 things you have to keep in mind while designing this, while considering this fast fading. Next one is the slow fading. Now, due to the Doppler spread, the rate of change of the channel characteristics is much smaller than the rate of change of the transmitted signal, which means that the receiver is moving at a very less speed. So, that is why we have considered the value that is known as the slow fading. Now, it occurs when Bs is far greater than Bd and Ts is far less than Tc. Now, Bs means bandwidth of the signal, this is the Doppler spread, Ts is the symbol period and this is the coherence bandwidth that we have seen. So, when the symbol period is far less than the coherence bandwidth, then this point we have considered, and when the bandwidth of the signal is greater than the Doppler spread, then Bs is greater than Bd. So, that is the it occurs in the slow fading case. So, these are the references that you can consider for this particular topic. In this lecture, we have discussed about different fadings the small scale fading and large scale fading. The basic idea is that when the distance between the transmitter and receiver is quite large and also the receiver is not moving in nature, that is known as large fading. In case when the distance between the transmitter and receiver is quite small and we are not again considering the Doppler shift of the receiver, then it is known as small scale fading. When the Doppler shift is considered, it is only considered in a case when the receiver is moving in nature and then also when the receiver is moving at a faster speed or smaller speed. When it is considered a faster speed, then it is known as fast fading. When it is moving at a very small speed, very less speed, then that is known as slow fading. So, that is fast and slow fading. Now, 2 types of fading we have considered on the basis of this multipath time delay spread, that is flat and frequency selective. So, in this case we have considered this channel bandwidth and signal bandwidth. The bandwidth of the signal, when it is smaller than the channel bandwidth, then that is known as flat fading, when opposite of that is known as the frequency selective fading. In case of this one, delay spread is smaller than the symbol period, that is known as flat fading, and when the delay spread is greater than the symbol period, then that is known as small scale fading. Now, this is based on the Doppler spread, this is fast fading, this is slow fading. In case of fast fading, high Doppler spread will be there, its coherence time is less than the symbol period, channel variations are faster than the transmitted signal variation. So, that is known as fast fading. In case of slow fading, channel variations are smaller than the baseband signal variation. So, that is known as the slow fading. So, that is why it is small scale fading. Then we have seen different channel characteristics, like it will vary from 0 to tau, which is having this rectangular kind of system, rectangular kind of waveform, that is the rectangular window. When it is passed through this one, then the signal got tapered in nature. Then in case of frequency selective, you have seen we have seen that this particular is having this parabolic shape and then it will be changed in this particular manner. Now, next is the fast fading. Fast fading is when the channel will the receiver will move at a very fast speed, and this is considered when the receiver is moving at a very small speed. So, this is all about today's lecture. These are the references. Thank you.